So yeah, I hope the screen is visible. If not, please let me know. So let's start. So this week's assignment is mainly on this addition of angular momenta and tensor operators and Wigner-Eckert theorem. So the main point of today's this week's session is that to appreciate the power of symmetry arguments. Like you do not need to perform detailed wave function integration calculations, but simply from symmetry arguments how to find some particular answers. Like this first problem, so given this matrix element, we can easily find this matrix element without performing any wave function integration calculation. So just from commutation relations, so that is what is meant by symmetry in very elementary sense. So yeah, using only these known commutation relations, we can directly find this directly find the answer to the boxed thing from the information given in the question. Okay, so let's start. Okay, so a matrix element is given, like it's the matrix element of the Z operator. So this is the position operator Z. So between the 4f and 4d hydrogen states. So 4f means so n is equal to 4 and l is equal to 3. So this is the 4f state. And 4d state is n is equal to 4 and l is equal to 2. This is the 4d state. Okay. So the matrix element of this Z operator is given as this. Is given as A. So we do not need to know what is A for this question, but A can be found by performing this wave function integration. So to actually find A, you actually need the radial part of these wave functions. So we will not do so here. So given that information, you have to find this another matrix element in terms of A. Okay, so let's begin. So this is the matrix element of Z that is given in question. We have to find a matrix element of Y. This is another component of coordinate operator. So we have to find the matrix element of this Y component. Okay. So as I said, state F. So this from elementary quantum mechanics in your class 11th and 12th. So we denoted the states as S, P, D, F, etc. So S is L0, P is L equal to 1, now D is L equal to 2 and F is L equal to 3. So it is those S, P, D, F states. Okay. So this 4D and M equal to 2 state can actually be written like this. So N equal to 4, L equal to 2 and M equal to 2. So so for your hydrogen atom problem, the Hamiltonian of the hydrogen atom problem has the eigenstates which can be characterized by three quantum numbers, right? L and M are L square and Lz quantum numbers, and N is the radial quantum number. So due to highly uh, due to high degeneracy present in that problem, we need these three quantum number to uniquely characterize each eigenstates. So for d m equal to 2 state is actually written like this in that notation. Similarly, for if m equal to 2 state, similarly for if m equal to 2 state is written like that. So n equal to 4, L equal to 3 and m equal to 2. Okay, so we have expressed these states for m2 and for tm equal to 2 in terms of NLM eigenstates. Now see, we have to find this matrix element of this y operator. So, and we also know that this is the commutation relation between Lx and z. So commutator of Lx and z gives you minus IH cut y. So this is one commutation relation. So this commutation relation will be very useful for this problem. See, so we have to find this matrix element in terms of A, and A is this matrix element. So that means to relate this y operator here and z operator here, we can easily use this commutation relation, because this commutation relation links z and y. So in place of y here, we will replace this with the commutator between Lx and z. So that is what I have done here. And there is this I by h cut factor in front that comes from the commutation relation. So in place of y, I have written the commutator between Lx and z. Okay. So for f m equal to 3 and for d m equal to 2. In between them sandwiched is the y operator. I'm sorry, what negative sign? So yeah, so you see this is minus IH cut y in the right hand side. So I have taken the whole thing in the left hand side. So that is why in the left hand side you have, so compare this. So y equal to I by h cut Lx z commutator. So I have brought the extra factors in the left hand side, and that is how your minus I got changed to plus I. So 1 by minus I is equal to I. So it is that thing, nothing else. So is it the thing you are asking or another thing? Okay, so yeah. Now doing nothing but expand the commutator. So commutator of Lx z, you know what you will get if you expand this commutator. Now we know, so we are actually used to to work with this L plus and L minus operator instead of Lx and Ly, because L plus and L minus have some simpler action on the L comma M basis gates, right? So we will write Lx in terms of L plus and L minus so that we can exploit that properties. So let us now see. So look at this term. So this will be the term where Lx will act on 4D m equal to 2 state first. So first Lx will act on this, then operator Z will act on this. So first Lx will act on this. Now let us find what will be the result of this operation. So for that, let us first write Lx in terms of L plus and L minus, and as we have discussed, 4dm equal to 2 is nothing but n equal to 4, L equal to 2 and m equal to 2. Okay, so now okay, so these are linear operators, so that means L plus and L minus will act on this gate separately, and finally we need to add those two contributions to get the final answer. So let us first look at L plus acting on n equal to 4, L equal to 2, m equal to 2. So what is the answer for that? So L plus acting on L equal to 2, m equal to 2. So this is the highest order state, right? So when L equal to 2, the maximum value of m is 2. And you cannot raise the state further to have higher m eigenvalues. So that means L plus acting on L equal to 2, m equal to 2 is 0. Okay. So we have to look at only the action of L minus acting on L equal to 2, m equal to 2. And okay, so if you remember the formula, so L minus acting on L comma m is okay, so that will decrease the m eigenvalue by 1 unit. So L minus acting on L equal to 2, m equal to 2 will be L equal to 2, m equal to 1. So decreasing m by 1 unit, and L is unchanged, but there is a non-trivial front factor, and that is h cut L into L plus 1 minus m into m minus 1 to the power half. So I hope you remember this front factor. So in previous 2 weeks I have discussed about them. But this week I have not written the explicit formula, but I have directly used that formula. So L into L plus 1 minus m into m minus 1 to the power half, and there is an h cut in front. So evaluate that and you will get this. So that means your answer is, so Lx acting on 4d m equal to 2 is h cut n equal to 4, L equal to 2, m equal to 1. So this is the action of Lx on the 4d m equal to 2 state. Okay, so similarly we can also find, actually we have to also find the action of Lx on 4f m equal to 3 state, because this. So we also need to find this. So you see the relation between these two. So if you just take Hermitian conjugation of this thing, you will directly reach this thing. So that is why let us first try to find the action of Lx on this gate, and then if you take Hermitian conjugation, you can directly get the action of Lx on this bra. Okay. So again, so let us write Lx in terms of L plus and L minus, and 4f m equal to 3, as we discussed, is nothing but n equal to 4, L equal to 3 and m equal to 3. Okay. So again we notice that L equal to 3, m equal to 3. That means it is a highest weight state. And that means L plus acting on L equal to 3, m equal to 3 will give you 0, because you cannot increase m any further. So for L equal to 3, the highest value of m is 3. So act with L plus on that state and you will get 0. Okay. So again, only L minus acting on this state will give you some non-zero result. And using that formula, so L into L plus 1 minus n into m minus 1. So using that formula, the non-trivial front factor will be this, to the power half, and in the gate the m value is decreased by 1 unit. So from m equal to 3 you reach m equal to 2. Okay. So the result of Lx acting on 4f m equal to 3 is this, h cut by 2 root 6, and the state is 4f m equal to 2. Now we have found all the basic ingredients that is needed to actually calculate this quantity. So let us write that this was equal to our commutator, matrix element of the commutator, this, and that was equal to this, nothing but I have just expanded the commutator. Now we have already found the action of Lx in the bra and gate states, so we'll just simply substitute those results. Okay, so for this part, so let us substitute this result. This is the result for gate, and we have to substitute the result for bra. Okay, so it is easy. So substituting this first part, you see Lx acting on 4f m equal to 3 bra will give you h cut by 2 root 6, 4f m equal to 2 bra. So just Hermitian conjugation of this relation. Okay, so this is your first term and this is your second term. Second term is coming from here. Okay, so Lx acting on 4t m equal to 2. We have found what is the result. This is the result. So the second term is 4f m equal to 3 and 4t m equal to 1, and sandwich between them is the z operator. So this is the thing, and we can see that this is actually 0. So this term is actually 0. How to see that? Like it can be seen like this. So we know that the commutator between LZ and Z is 0. So LZ and Z commutes. So put the commutator here between these two states. Since the commutator is 0, the matrix element is 0. Nothing to think about. And then expand the commutator, and then you will get two results that you have to subtract one from another, and you will get 2h cut 4f m equal to 3 and 4d m equal to 1. Sandwich between them is z cap, and this total thing is equal to 0, and that means this matrix element have to be 0. So this is easy proof. Yeah. So this was possible because LZ and Z commuted with each other. That is why it was possible to show that this is 0. So another thing is that since LZ and Z commuted, that means different eigenvalue of LZ will also diagonalize Z, right? Because LZ and Z then will be simultaneously diagonalizable. Right? Remember that formula? Like if two Hermitian operators are commutating, that means they are simultaneously diagonalizable. That means so eigenbasis of one of the observable will also diagonalize another observable, the other observable that is commutating with the previous one, right? So m equal to 3 and m equal to 1, they are eigenbasis of LZ, right? So since they are orthogonal eigenstates of LZ, that means they also diagonalize this Z cap operator that commutes with LZ, and thus, and since these two eigenvalues are different, like they are mutually orthogonal, that means the matrix element of Z between these two eigenstates that correspond to two different eigenvalues of LZ will be 0. So the matrix element of Z between two eigenstates corresponding to different eigenvalues of LZ will be 0 because of the simultaneous diagonalizability property, and which comes from the fact that LZ and Z mutually commute. So we have just shown that this part is 0, and we are only left with this much, and the answer for this matrix element is given in question as A. So this part is given as A in question. So simply substitute and you will get this as your final result. So I root 3 by 2 A. So this is the final answer to the question. So okay. So this was a question that was solved using the Wigner-Eckert theorem, but in more detailed fashion. So you can also try to choose to solve this problem directly using the Wigner-Eckert theorem. But here I have decided to go through the intermediate steps. So in this way, the thing is hopefully more clear. So if you have any question, please ask. Okay, fine. So let us move on to the next one. Okay, so this is a question from the assignment, but I do not know why the options are given incorrectly. Like, the question is, find the maximum degeneracy of states when we add angular momentum j. Okay. So find the maximum degeneracy of states when we add angular momentum j1 equal to 4 and j2 equal to 2. So so if you add these two angular momenta, what do you expect? So the after addition, the j values, we expect it to lie between this range, right? This is the range for the total j values. Like it is less than equal to j1 plus j2, but greater than equal to the difference between j1 and j2. So by this logic, so here j1 is 4 and j2 is equal to 2. By this logic, j lies between 2 to 6 with steps of 1 unit. So j cannot take half integer values here. So j takes only integer values, and maximum is 2, minimum is 6. Sorry, maximum is 6, minimum is 2. So the possible j values are 2, 3, 4, 5, 6. So as you can understand, so the j equal to 6 value has highest degeneracy, and of course this degeneracy is 2j plus 1, and that is why the answer should be 13. But there is no option as 13, so I do not know what to do. So there is nothing complicated, so you have to just use this knowledge. So what is the range of allowed values of j, and just substitute the values. So you will get j to be equal to 2, 3, 4, 5, 6. So the maximum degeneracy will correspond to the j equal to 6 state, and j equal to 6 state has degeneracy 2j plus 1 means 13. So this should be the answer. So this is just a fancy notation, so I do not think it is necessary. Okay, so I will not discuss about this. So there is nothing more to this question. So if you have any doubt, please ask. Otherwise, let us move on to the next question, which is interesting. Okay, so we move on to the third one. So I hope you are familiar with the notation, right? So and tensor operators, etc. So let S KQ and TKQ are two irreducible tensor operators of rank K. Okay. and so q can take values from minus k to plus k, just like your m eigenvalues. So here q is like m and k is like l. So compare with that notation. So skq and tkq are two irreducible tensor operators of rank k. Now show that the following is a scalar operator. So we have to show that this is a scalar operator. So summing over q, q goes from minus k to plus k, like over the full range, and this is minus 1 to the power q, this is tkq, but this is sk minus q. So this is the operator given, and you have to show that after summation the whole thing is a scalar operator. So the alternate definition for a tensor operator is this. So if tkq is a tensor operator of rank k, then this is the definition of the tensor, like the commutator between Lz and tkq is qh cut tkq. So just compare with the eigenvalue relation of Lz. So it looks like an eigenvalue relation of Lz, right? But this is for operators, so this is just for remembering purpose. So the commutator between Lz and tkq is qh cut tkq, and then there are these two commutators. These are the analog of the L plus L minus actions. So they are like almost same. Okay, the front factor etc are exactly same with the 1 when L plus and L minus acts on Lz eigenstates. So this is the same front factor, and if you see this, the q value is increased by 1 if you take commutator with L plus, or decreased by 1 if you take commutator with L minus. So the action is exactly same as when L plus and L minus acts on Lz eigenstates. So this is the definition of tensor operators of rank k, and of rank k, and q denotes individual components of the irreducible tensor operators, but the rank is k. So when we compare, so as I said, k is like L and q is like m. Okay. Now using this definition, we have to find this same relation for this operator given in question as omega. So we will find Lz omega, okay, and L plus omega commutator and L minus omega commutator. So after we will find these three commutators, we will compare with these three definitions to actually find what will be the value of k for that omega and value of q for that omega. and then we can conclude uh, whether omega is a tensor operator, and if it is a tensor operator, what is its rank and which component is it. So let us begin with the commutator between Lz and omega. Okay, so we have to just use this definition, this relation, and the distributive property of the commutators. Like, you can bring this summation sign outside the commutator, right? So you have to now perform this commutator. Now so I hope you know how to take commutator of like C, comma AB, like this kind of commutators. So C, commutator of C and commutator of this composite operator AB is, so commutator of CA multiplied by B and A multiplied by commutator of C comma B. So that relation should be used, and remember, so this part is Lz TKQ commutator, and Sk minus Q is is kept in the right hand side of the commutator, and this is the second term where where you are using Lz Sk minus Q commutator, and TKQ was kept in the left side because this was originally on the left side of Sk minus Q. So just using that commutator formula for composite operators. So Lz and commutator of TKQ is QH cut TKQ, and commutator of Lz and Sk minus Q will be minus QH cut Sk minus Q. Just remember this formula, and we find that they are exactly equal and opposite to each other. So that means this is 0. So we have our first result. So the commutator of Lz and omega is found to be 0. Fine. So that was the easy part. Now let us try to calculate this commutator. Commutator of L plus and omega. Again, so we will bring the summation sign outside the commutator, and then again we will use the commutation relation for composite operators, and we will use this definition. So this definition for L plus. So when L plus acts on TKQ, you get this. Just compare with this definition. There is nothing to understand, just algorithm. So commutator between L plus and TKQ is this. fine. And then there will be another term in which you will be finding the commutator between L plus and Sk minus Q, right? So L plus and Sk minus Q. So in this formula for L plus, you have to put minus Q in place of Q. If you do so, you will get this term. So look carefully, here it is minus Q into minus Q plus 1. So just put minus Q in place of Q. So there are these two terms. Fine. Now we have to actually perform this summation to proceed. So let us take this first term. So let us try to evaluate this term. Okay. So how to perform this sum? And we want to actually compare with this term, right? And you see there is a difference. Like in first term, you have, in this term you have t k q plus 1, but in the second term you have t k q. So there is a mismatch. The first term you have sk minus q, but in the second term you have sk minus q plus 1. So there is a mismatch. So how can these two labels can be brought equal? So let us, like where it is, so q, let us take q is equal to q dash minus 1. So it is like changing of variables in integration. So we do change of variables in integration, right? And yeah, hello. Okay, so we do change of variables in integration, and when we do change of variable, the range of integration also needs to be changed, right? So we will now perform the change of variable from q to q dash. So let us substitute q in terms of q dash. So just use this relation. So just substitute q dash in place of q using this change of variable relation. Do so. So now if we compare these two are looking almost same, other than the fact that here you have q but below you have q dash. And we can also further see, okay, so now let us perform this change of range. So if q dash minus 1 is from minus k to k, then q dash is of course from minus k plus 1 to k plus 1. So this simple change of change of range of the integration variable. This is fine, coming from previous line. And now we notice that this factor, so q dash minus 1 multiplied by q dash, can be expressed like this, right? So can you observe the similarity? So these two are exactly the same. These two are exactly same. Okay. So now let's look. So this term and these two now look exactly similar, other than the fact that uh, here you have q, but below you have q dash. But other than that, I mean, they look exactly similar. So there is another trick, or not trick, but it is quite trivial. So now, like we do in integration, so sometimes for comparison purpose, we rename the integration variables. Like it does not matter what you name your dummy variable, right? You are going to sum over the dummy variable. So dummy variable takes some specific values. So we can easily rename our dummy variable from q dash to q. So just rename the dummy variable q dash as q. So in this step, we are just performing some renaming of dummy variable. Okay, and after performing this renaming of dummy variable, so of course, as we discussed, they are exactly same now, but notice there is minus to the power q, there is minus to the power q minus 1. So only difference of a minus sign. So they are off by a minus sign. Other than that, they were exactly the same. Okay. But another thing that is different is the range. So here q is from minus k plus 1 to k plus 1. But here q is from minus k to k. So how to account for this difference in the range of summation variable? Well, we see. So if you put q equal to k plus 1, so put q equal to k plus 1 here. What will you get? So if you put q equal to k plus 1, this front factor will be 0, right? You can easily check that. So this front factor will be 0. That means q equal to k plus 1 will not contribute to this sum. So we can easily write the upper limit as k, because the k plus 1, q equal to k plus 1 will not contribute anything to this sum. So what to do about the lower limit? This is minus k plus 1. We can also see, so if we put q equal to minus k, this factor again vanishes, right? Put q equal to minus k and you will see this factor will give you 0. So that means we can safely bring in a q equal to minus k term without altering the final result, because the term that you are bringing in is actually 0. That is why it does not change the final result of the summation. So we can safely bring the q equal to minus k term also. Thus, our summation is now from q equal to minus k to plus k. And this thing, now let us compare. So now we have brought the range of the summation exactly to this one, and now let us compare. So we are calculating this term, this highlighted term. and this is the result. This is the result, and now we can see that this is exactly equal but opposite to this term, right? Exactly equal and opposite because there is this extra minus sign. So that means when you add these two, you will get a 0. So the commutator between L plus and omega is 0. So, and similarly, if you use the L minus commutation relation from here, so if you use L minus commutation relation, you can similarly show that L minus omega commutator will again be 0. So that means we have three relations. So Lz omega, they commute L plus omega and L minus omega. These two commutators are also 0. So these three commutators, all of them are 0. So comparing with these three relations, we can see that omega is nothing but it must have k equal to 0. So that means omega will be a rank 0 tensor operator. So omega will be a rank 0 tensor operator, and rank 0 tensor operator means a scalar operator. So that is why omega is a scalar operator. So the terminology is like this. So rank 0 tensor operator is scalar operator, rank 1 tensor operator is vector operators, and from rank 2 onwards there is no new name, but they are called simply tensor operators. So scalar, vector, and from rank 2 onwards they are tensor operators. So okay, so that is how you proved that omega is a scalar operator. So if you have any question, please ask. Okay, so don't think there is any question. So let us move on to the next one. So the question is, write the product of the position vector components xz in terms of spherical rank 2 tensor components. So we will use these definitions. So we will mainly use this definition. And in the question it is already given that write them as a in terms of rank 2 tensor component. That means we are already told that k is equal to 2. So we already know k is equal to 2. So we just have to use these relations to actually find what will be the corresponding values of q. So nothing much to do, just keep taking commutators with LZ. So let us just begin by taking the commutator with LZ. So commutator of LZ and XZ, what is it? So you know the commutator of LZ and X is IH cut Y. This is IH cut Y, and commutator of LZ and Z is 0. So the total commutator of LZ and XZ is IH cut YZ. Okay, so that was one thing. But we see it does not look anything like this, because LZ TKQ is QH cut but TKQ. So the component would be same. So we should have got, so acting on XZ, LZ acting on LZ and XZ commutator, if the right hand side was also XZ multiplied by some constant, then we would have said that XZ is a irreducible spherical tensor. But that is not the case. So after taking commutator with LZ and XZ, we find that the right hand side is YZ. So it is changed. So what to do? So let us now take the commutator with YZ then. So commutator of LZ and YZ. Similarly, we find the answer to be minus IH cut XZ, because the commutator between LZ and Y is minus IH cut X. So this is the commutator, but again we see that YZ by itself is also not a irreducible spherical tensor operator, because commutator of LZ and YZ does not give you back YZ but something different. But we notice that this combination, so if you add these two up, so XZ plus IYZ, you get this answer. A constant multiplied by XZ plus IYZ. This means XZ plus IYZ is an irreducible spherical tensor, because so in the right hand side we are getting back the same thing, and the Q value is 1. Compare with this definition. So Q value is 1. And similarly, there of course you have taken plus I, so you will also take the minus I. So commutator of LZ and XZ minus IYZ gives you back this XZ minus IYZ multiplied by some constant. And you can recognize the Q value to be minus 1. So that means this. So we are already told that XZ is a rank 2 spherical tensor. So it is a rank 2 tensor. So similarly YZ will also be a rank 2 tensor. So they are already rank 2 tensor, this much we know. And now using this commutation relation, we have found the corresponding Q values. So the Q value of XZ plus IYZ is plus 1, and Q value of XZ minus IYZ is minus 1. So you can write it like this. So T is some spherical tensor, which of which plus 1 and minus 1 components are xz plus minus iyz. So of course now it is easy to find xz in terms of the irreducible spherical tensor components. So this is the answer. And of course you could have also found the answer of the yz. So there will be just a minus sign in between them and a factor of I in front. So okay. So remember, you need to remember that this is not a definition. So I used this and this is wrong. So the definition is only in terms of Lz and L plus minus. So these three commutation relations. But this is not a definition. So you must not take commutation with L square. So that is not the definition of irreducible spherical tensors. So you have to only compare with the commutators with Lz and L plus minus. Okay. So this is a lesson. Similarly for other terms also, like this x square minus y square. So of course, as by now you understand that all of them, like when this xz, yz, xy, x square, y square, z square. So when the total power of these polynomials is 2, so they correspond to rank 2 tensors. So all of the possible linear combinations of them will be components of some rank 2 tensors. So all of them are rank 2 tensors. So x square minus y square will again be a rank 2 tensor. But we have to find the q components. So again, so it's nothing difficult, but you have to just find the commutation relation with Lz. So Lz, x square minus y square, gave you xy in the right hand side, and then Lz and xy gave you back y square minus x square. Now take some combination. Take some combination like this. So that means x square minus y square plus 2yxy is a component of an irreducible spherical tensor. And this is q equal to 2 component. Similarly, this is also a component. This is q equal to minus 2 component. So like this. That means this is, so that means there this plus minus 2 components with of the rank 2 spherical tensor. So you can just take the linear combinations to extract these things. So that is how you solve these problems. Now there is another way, so without going through these lengthy commutation relations, you can directly, like when, so if you are asked to find the spherical tensor corresponding to this xz, like corresponding to the position coordinate operators and their multiplications, so you can simply use this trick, like write xyz as in spherical polar coordinates. The total power of r will be the rank of the tensor. Okay, so xz you have r square. In yz you have also r square. So that is why they are rank 2 tensors. And now look at this phi. So xz is r square sin theta cos phi. And you know your spherical, from your knowledge of spherical harmonics. So YLM, so the phi dependence of YLM is e to the power im phi, right? So we should use that knowledge here also to make these irreducible spherical tensors. So YZ is proportional to sin phi. So that means if you add these two up, you will get this r square sin theta cos theta e to the power plus minus I phi. And as I said, the spherical harmonics YLM has phi dependence as e to the power im phi. So we have to just bring the phi dependence in the form e to the power im phi. Okay, so bring by observation into e to the power im phi form, and from there you can readily recognize the q values of the spherical tensor, like zx plus I plus minus izy is r square sin theta cos theta e to the power plus minus I phi, and that means they correspond to q value plus 1 or minus 1, and rank is 2 because of this r square, as I said. So this is the trick to find the answer quickly. So similarly, y square is this sin square phi, x square is cos square phi, that means x square minus y square is cos 2 phi, and 2xy is sin 2 phi. So that means x square minus y square plus minus 2ixy will be this e to the power plus minus 2 I phi, and that means their q value will be plus minus 2, as we have found here using these lengthy commutation relations. So this is the trick to quickly reach the answer. So this concludes the discussion on this question. If you have any doubt, please ask. Okay. Before the discussion of question 5, let us quickly go through this small question. So, relation between parity and angular momentum. So, does the parity operator commute with angular momentum operator? So in classical mechanics, we know what will be the answer, right? So angular momentum is r cross p, and parity is space inversion, right? So your x is changed to minus x. So r is changed to minus r. What about p? So p is mv, velocity, and v is dx dt, right? Instantaneous change in velocity. So p is dx dt. So if x is changed to minus x, that means dx by dt, sorry, dx dt is changed to minus dx dt, and that means p is then changed to minus p. So under the operation of parity, r goes to minus r, p goes to minus p. So that means r cross p will remain same, because minus minus will cancel each other. So the angular momentum r cross p will remain unchanged under parity. So this is from the knowledge of classical mechanics. And that is why, since L is a vector, but it does not change sign under parity, so that is why L is called a pseudo vector. So a vector that changes sign under parity is a real vector. A vector that does not change sign under parity is called a pseudo vector. So L is a pseudo vector. Another pseudo vector is magnetic field. Magnetic field is another pseudo vector, but electric field is a proper vector. Yeah. So now let us see what happens quantum mechanically. So the quantum mechanical angular momentum operator is this same r cross p, but now r and p are operators. And this can be written like this fancy relation, so component wise. So you know the cross product can be expressed using this Levi-Civita symbol, epsilon ijk xj pk, and summation over j and k is implicit. I mean they are there, but I have not written. So this is called the Einstein summation convention, where repeated indices are summed over. So the ith component of the angular momentum is written like this. Okay. Now we know the operation of parity operator. So this, so remember, so x is a operator. So on operator, the parity will act like this. So px p inverse. So in quantum mechanics, some transformation acts on an operator like this. So p operator p inverse. Okay. So px p inverse is minus x, because parity is space inversion by definition. So x must change to minus x. And this relation also holds. So under parity, p also changes to minus p. So this was actually the subject of discussion in some assignment. So this was some assignment question, I guess, on week 5 probably. Week 5 or 8, I don't remember, but we actually showed that under parity, p changes like this. So please revisit that assignment question if you have forgotten how to derive this relation. So p actually have this property under parity. So now we have to check what about this. So p li p inverse, what will it give us? Will it give us plus li or minus li? So we have to check this. So in place of li, just use the definition in terms of Levi-Civita. just use this definition. Epsilon ijk is some number, not an operator, so it is some scalar in the space of operators, so we can just simply bring it outside. So the moral of the story is a parity operator will not act on epsilon ijk. Okay. So p x, so now between this x and pk, so here let us insert, so this is, you can think this void as an identity, right? So you can introduce identity anywhere you want. So let us introduce an identity and let us write that identity as this P inverse P. Okay. Now let us recognize this term separately. So this is a, and you know the operator multiplication is associative, right? So you just have to respect the orders, but you can multiply them anytime you wish. So this P xjp inverse, remembering from this, will give us this minus xj, and then this other term comparing with this will give us minus pk, and this, there are two minus signs that will cancel each other, and finally you get li. So that means p li, p inverse is equal to li. Okay, so this implies simply this, like multiply both sides by parity operator in the rightmost place, and this implies that parity and angular momentum commutes. So we already anticipated this relation classically, but using quantum mechanics, this is how you have to show it. Okay, so if you have any question, please ask. I don't think that is the case. Otherwise, let us try to add two angular momenta. Okay, so let me ask you one thing. So have you practiced how to add angular momenta or not? Like addition of two spin one, or like L equal to 1 and spin equal to half. So have you practiced, or okay, so if not, let us quickly go through this. Like addition up to spin 3/2 angular momentum, and how to find those Clebsch-Gordon coefficients. Okay, so when we add two angular momenta, we express this Jm states. So J is total angular momentum and M is the total uh, jet component of the result of the addition. So we express this Jm states as linear combination of these states. So these are individual states, S1 M1 and S2 M2. These are the states of the individual components, and these are the state that describe the result of the addition. Okay. So let us begin. So we already know. So J mean will be 0 here and J max will be 3, because J mean is the difference of two angular momenta that we are adding, and J max is J1 plus J2. So here both of them are 3 by 2. So J mean will be 0 and J max will be 3. And we already know, we also know this total M is equal to just the sum of M1 and M2, the sum of individual components. So M is M1 plus M2. So what we do? So we actually begin with the highest weight state of the highest angular momentum. So J max is 3. So we will begin with J equal to 3 and M equal to 3. Right? So, and we said that M is equal to M1 plus M2. But we are adding two spin 3 by 2 spins. So when can M take the value 3? So this is possible only when M1 is 3 by 2 and M2 is also 3 by 2. So that is the only possibility, because M1 and M2 both have maximum values as 3 by 2. And only after this addition we can get M equal to 3. So this is the only possibility. So we have to identify this J equal to 3, M equal to 3 state with this state. When M1 is 3 by 2, M2 is 3 by 2. Okay. So this is the starting point, this recognition. And now you have to keep acting with the lowering ladder operator on both sides. So lowering ladder operator J minus. So you know, so J minus will be sum of the lowering ladder operator of both spin components of both spins. So this is actually direct sum. So J minus is equal to the direct sum of S minus 1 and S minus 2. So direct sum of lowering ladder operators of both of the spins that we are adding. Okay. So let us now act. Okay, and remember this notation. So these states, so this is a direct product state, this is a direct product state. Okay. And the direct sum acts on this like this. S minus 1 acts on the state 1, so state of the particle 1, and nothing, I mean identity acts on the state of the particle 2, plus this identity 1 acts on the state of particle 1, and this lowering ladder operator of particle 2 acts on the particle 2. So this is the meaning of the direct sum actually, like this. Like they do not simultaneously act on, like you may have thought that S1 minus will act here, direct product S2 minus will act here. So that is not the case. So this is the meaning of the direct sum. And J minus on the left hand side acts as usual. So evaluating all these stuffs using our lowering ladder formula, like that front factor, non-trivial front factors. So remembering all of those stuffs, we get a result like this. So this is J equal to 3, M equal to 2, expressed as a linear combination of M1, M2 states. So this is the shorthand notation usually employed. Like, so these states are denoted as these shorthand notations. Okay. Now you just have to keep acting with this J minus in left hand side and in right hand side with this direct sum. Okay, and every time you will have to keep track of this front factor that arises when you act with these lowering ladder operators. Okay, so nothing. So this is just an algorithm. So this is this. Now act with J minus again and this. So keep doing that and you will get the answers. Okay, so once you have suppose once you have the highest weight state for J equal to 3 and M equal to 3, this is the highest weight state for J equal to 3, you can directly find the J equal to 3 but with other M states directly by acting with these lowering ladder operators. Okay, so once you know that your J equal to 3, M equal to 3 is this, all you have to do is just to act with lowering ladder operators until you reach this, the lowest weight state with J equal to 3. Okay. So that much is fine. But what to do? So you know, so J equal to 3 is not the only possibility. There will be states with J equal to 2 also, as we know. So, and J equal to 2 will have M equal to 0, plus minus 1 and plus minus 2. So how to find J equal to 2, M equal to 2? So there are possible. So unlike M equal to 3, where the only possibility was for both of them to take M equal to 3 by 2 and M to 3 by 2, for M equal to 2 there are multiple possibilities, like M1 can be half, M2 can be 3 by 2, or M1 can be 3 by 2, or M2 can be half. So we do not uniquely know which will be the state corresponding to j equal to 2, m equal to 2, but we can use the knowledge from our j equal to 3 construction. So the j equal to 2, m equal to 2 state has to be orthogonal to j equal to 3, m equal to 2 state. Right? They have to be orthogonal because they correspond to two defined value of the Hermitian operator L square. So that is why they have to orthogonal. And as I said, m equal to 2 is possible only when m1 is half, m2 is 3 by 2, or the opposite. So the so this will be a linear combination of these half, 3 half, and 3 half comma half. This will be a linear combination of this. So we have to find a linear combination of this half comma 3 half and 3 half comma half that is orthogonal to this state. Okay. So we easily find the orthogonal linear combination, the linear combination that is orthogonal to this state to be this one. So we easily find that. Okay, so that is how we find j equal to 2, m equal to 2. Now once you have found j equal to 2, m equal to 2, keep acting with the ladder operators, lowering ladder operators until you reach j equal to 2, m equal to minus 2. Just keep using the lowering ladder operator on both hand side. Now j equal to 1, m equal to 1 is also another possibility, and clearly it has to be orthogonal to both of j equal to 3, m equal to 1, and j equal to 2, m equal to 1. And moreover, so m equal to 1, when is m equal to 1 possible? So when m1 and m2 is half comma half, or minus half comma 3 half, or 3 half comma minus half. So m1 plus m2 have to be equal to 1, so only when m can take the value 1. So j equal to 1, m equal to 1 has to be a linear combination of these three states. Okay, and this linear combination will have to be orthogonal to both of these two states. Okay, now just find the inner product and demand the orthogonality. You will see that you are getting these two relations. One is this, another is this. Also demand the normalization property, a square plus b square plus c square equal to 1, and then you will get the unique solution that j equal to 1, m equal to 1 is this. So now once you have found the highest weight state, again you can reach the states all the way up to the lowest weight state using the lowering ladder, and now finally remain to find this J0 M0 state. Again these have to be orthogonal to all of these three states, and we know it has to be linear combination of these four states. So how to make total M0? There are only four possibilities. So all of the states that can lead to m equal to 0 will appear in the linear combination, and we will have to find the coefficients of that linear combination by demanding the orthogonality property, and finally the normalization property. So use that and you will get this result. So that is how you add two angular momentum. So that was rather quick, but I hope you understand how to actually perform the calculations. So if you have any question, please ask. So this is the last question of the session. And if not, okay. Okay, so I will end this session. Thanks for joining. So next week will be the last session for this course. Okay, so I am ending this session.